Hello everyone, in this video we'll learn how do we create a tree structure in C++. You may come across there are a lot of trees are there like binary tree, AVL tree, red black trees and N-ary trees. This is a N-ary tree. N-ary tree is a generic form of trees. N-ary tree means there will be a node and there may be n number of child attached to that node. Here you can see node 1 is there, here 2 children is attached, and with node 4 there are 3 children is attached. In node 7 there is 1 children is attached. In an ideal binary tree there will be only 2 nodes. There will not be a 3-4 nodes. There will be a right and left, but this is a generic form of tree. And in this video we'll learn how to create the tree structure in C++, and we just traverse through these nodes using DFS algorithm. Now let's see how this tree looks like. First of all, we may create a binary tree. So let me just create a one binary tree here. This application you can see the nodes in a tree structure. So let me just delete the existing data. You don't need this count. I'm just giving 1 to 2, 2 to 3, 2 to 4, and a 3 to 5, and a 3 to 6. And I'm going to arrange this config, arrange as a tree. Okay, here 1 2, some number I have to give. 1 to 3 I'll give. Arrange as tree. So under 2 also should be there. So from 2 to 7 I can give 2 to 7. This kind of a structure is a binary tree structure you would have studied in your data structure and algorithms, but then it's like it's a kind of an N-ary tree also. There are 2 or maybe 1 or maybe n number of children can be there. I have some test data. I paste that in the graph data here. We erase this 8, so there's this many. We'll arrange this as a tree, and here you can see this N-ary tree. So what I'm doing is I have to just print these nodes using some algorithms. Okay, let me just download this as picture and I'll import this. Okay, now the first node, it's called root. As you know this first node is called root. And these nodes are called children nodes. This is C, this is C, and this is C. For this children, what the above node is called parent, so it's called written as parent. So the last node, which means don't have any children at all, this is called leaf. These are some of the terminologies involved in tree structures. So how do we create this tree? So here you could have seen this. We are building a link structure. We are linking 1 and 2. This 1 is linked with this 2, and this 2 is linked with this 3, and similarly we linking 1 and 4, 4 5, 4 6, 4 7, and 7 8. This is a kind of a representation. Is the first is a U and second is V. It's namely called U edge, and this is V edge. This is U and this is V. The same thing we are going to represent in the code. So how do we do that? Is you can go to the IDE. Here I have some basic setup. I just import as iostream using namespace int main and return 0. In this video we are using adjacency list. Adjacency list, I'll explain this. In this one, we are taking a node 1. What are all nodes we attach to this node? We are taking and adding into one list, which means you have some table here. I'll draw one table. Here I'll switch that colors to green and outline to blue. Here I have node 1. I'll increase that font. Here I have node 1. What are all the nodes I have attached to that? I'm representing it in a list 1 and 3. We can consider this first column as a parent node, and these are all the nodes attached to it. Here I'm changing this color as blue, and these and all will be this color, green color. So in second node, there are how many nodes are attached? Is 3. And in node 4, how many are attached? Is 5, 6 and 7. So I'm writing 5, 6 and 7. Here with this 7, node 7, I have only node 8. So I need this kind of a representation in the code. So these are all the node structure. These are all the information that I got from this data, graph data. This used in V structure, one having 2, and 2 having 3, and 1 having 4. Those kind of representations I represent in this kind of list. This is called adjacency list. You can namely call this as adjacency list. I make it as sticky note. Adjacency list. Okay, this representation is, how do we do that to achieve this in C++ is using vectors. So I need a vector and an array. So vector representation of int, and I need an array. Actually this structure from here, this row is literally called as vector. We know that each row we want, we need to declare it as an array. So I need vector and int of array. So I move back to the IDE. I need total number of how many lines are coming for me. So I just declare as int as count, and I get that count at cin count. Next, I need that adjacency list representation. So what I'm doing here is I'm how to first import the vector class, vector preprocessing. I will include header called vector. Here in line number 8, you can type vector of type int, and you can give an array adjacency. You can just give adjacent, and inside of this you have to give some numbers. So I'm just giving as some 1000. You can give any number but not high numbers. It's literally like a memory you're utilizing, so you should not give a huge number. So it should not be like e power 10 and all. You should not give. You have to give only the up to 1 into e power 6. This is the utmost. That means 1 million vectors you have initialized like this. How you have these numbers? You have this 1 million rows. This is one row, second row, third row, fourth row. Like you have 1 million rows you're initializing, but it does not carry any memory. Uh, After you're filling the values only, it can hold the memory. It's expected the integer to be there and there, so I cast it as int. If you want, you can directly like write like 1000 as 6 zeros. Okay, now my adjacency list is ready, and I have to read that edge each time. So I'm declaring two more variables like u and v, u comma v here. and there will be, for a tree there will be n minus 1 nodes. I have here 8, so I'll what the number of edges will be, n minus 1. So edges equal to n minus 1. This is the formula you must remember. Here I have 8, so I'll have 7 edges. 1, 2, 3, 4, 5, 6. So okay, if I don't have these many edges, for example I have less than this, so it will come as an one node will be isolated. You can see here I have 8, but I'll just remove this, but you can see this will not be there at all. For example, you can write 1, 2, 3, 4, 5, 6, 7, 8. You can notice this 8 is floating somewhere. That means that's not a part of tree. So you must give n minus 1. It should come a perfect tree. So 7 to 8. That will be the perfect one, and it is attached to this node. Okay, I have one more node edge. What will happen? That will come as graph. For example, I have node like 6, I have edge like 6 to 8. This is not a tree. Here we have some looping, so this is not a tree, it will become a graph. So we must have this edges as in minus 1. So I giving for a type as int and count minus 1, and inside of it I just get c in. First is u and second is v for each time, and each time I'm pushing back that into the vector, corresponding vector, which means I'm taking adjacency list adj of u dot pushback. We are pushing back each time. You know this, when we encounter a new one, we add at the back of this list. We added each, after adding 2 we added 3. We didn't add in middle or front or anywhere, so we have to push back of v. We are just push back. So we just creating one time. We have, for when we encounter this one, we first using as a array index, and then we are adding at the back. We didn't mix it up. Like why you didn't write u comma v or v comma u? Here the same thing. We didn't write this kind of syntax. This is for the undirected graph. We are writing a directed graph. You can see this arrow here. We should have written arrow. This is arrow kind of structure, so we have to travel from one side. If it's an undirected graph, you must handle those cases as it should not, as what node that you're visiting, you have to maintain that visitor array. So I don't want to visitor that array, but will come in the upcoming videos. So we just give it as directed graph, and we have only one edge, so I'm just giving from 1 to 2. So I don't need this third line number 13, so I'm removing. Okay, now we just created array, created the tree. How do we see this is correct, or how do we traverse in this? Okay, I am for the traversing, I'm creating one more function called DFS. You know, this DFS means depth first search. First first and the search, depth first search. Depth first searches, we are going deeply inside after choosing one path. Here I'm deleting this one, and I'm removing this all. Now I'll import this new image. Okay, this image, we choose depth first search means we have to go deep inside, I said. So we have this, we've chosen this one as 1. and first we select the smallest number because we are giving us this order. I've given this small order, so small number order 2, and then only 4, like that I have given. So we have to follow that order. Where is that? Yeah, here 2 and 3. You can notice this is an incremental order, so I have to use in this order only. So after choosing one, I'm going to 2, and deep inside of it, I'm going depth 3. So my first answer should be displayed is 3, and then I'm coming out of it, and I'm getting 2. After I'm going inside, after this, once 2 is inserted, there will be 4. So 4 is also, it's taken, and in this, next is 5, and next is 6, and next is we're going inside and coming straight away to 8, and then 7, and then 4, and then 1. Okay, this is the order we have to get. Okay, let me just first write the code, and then I'll explain with the stack, this stack, how this inserted in this tree, or how the stacks works in the DFS algorithm. Okay, I just give it as depth first search, and I have to pass this adjacency matrix adj adjacency vector. We have to type the return type vector of int, and it's an adj array. And what is the root? In this example, we are treating the one as root, as a picture. In the N-ary tree, there can be anyone, it can be a root, but since it's a directed, and here no incoming edges, so we just give this as a root. Okay, I just type it as root, and let me just return 0. Okay, here let me just straight away type the program. We have to take each and every line of we have to just give a for int vertex in adj of root. Since it's a character graph, I no need to give anything, so just DFS. Here we have to give the adjacent matrix, and we have to give the vertex to pass. I just give brief explanation of this DFS depth first search, and we have to write cout. Here that root will print indel. Okay, now we move back to the explanation. Let me just right click and execute this code. What the output we get is, if any changes are there, we'll make those changes. After writing the function here, I have to call depth first search. Here we'll write that adjacency matrix, and I'm giving the root node as 1, initializing. Okay, now run the code. I copied the data and paste it. Here the output is I just write a output line here, cout, and depth first search, and indel. Right click, run code, paste. Okay, this depth first search is 3, 2, 5, 6, 8741, the same order what I have written at the time of iterating it. Here I have to change this as 4 because we don't have link between 1 and 3. So 2 and 4 I've written. Okay, how this program works and how these numbers are printing, and I'm explaining with this stack, this programming stack. It's internally maintained in the computer. We no need to write up. When you heard of the word snack, you come across the terms like push, pop, and there are a lot of terminologies associated with the stack, but the actual computer itself will take care of those things. We no need to care about inserting and popping it up. We have to write just a perfect program to iterate that. And it's like a bookshelf. After keeping a book at base, you're not inserting at the end of it. It's like a slab. You're keeping the books just above the book, one by one by one by one. Okay, now first line at line number 24, we pass this as adjacency matrix, and one is literally a root node. Here I have taken one as a root node, so we have one as passed as a root from this line number 24. So actual flow how it is works is it will take first count as this number 8, and we initialize the vector, and we each and every each that means n minus 1 time we just read this u and v 1 2 3 4 5 6 and 7. 7 times we read this, and for adjacency matrix of u we are just pushing back at the end. For particular node 1, when we take 1 we keep it as 1, and we are adding the 2 at the end. In this example also matrix adjacency list also, here after 1 is taken we'll insert the 2 here. We'll not switch back like 2 we didn't add 1, but wait, this is a directed graph. You can see this arrow mark. So we are just adding and place 1 and the end 2. Could just let me clear this all marks. Okay, after that we go to this star for depth first search function. We'll pass and it will directly goes to here. Okay, now we just got a reference of this adjacency node and we got root as 1. So this is a kind of advanced for loop that the line number 7. This is a kind of advanced for loop. This it's colon syntax you may come across this kind of 1 to n iteration for loops, but this is for just what are all the numbers are there. I don't need their indexes, so when I need the index I'll just give it as I and all, but I don't want those. I just need to iterate by the order what I have inserted. I just have to take those numbers, that 2 and 4. So I'm using this for loop. So adjacent in vertex colon adjacent of root. Here whatever the number is coming, I'm just taking of that and I'm finding what are all the elements are there. First I have 1, so here I have 1, so I just going these numbers what are all there in this list. First number is the actual root we'll take, and these are all these numbers in that for loop content. One by one it will, after 2 first it will take 2 and then 4, and then if anything is there it will go ahead, and or if it is not there it will come out of it and finishes. And then it prints the root and then it returns the 0. The return type I've written as int, it returns 0. So okay, now the actual thing is what we need to understand is inside of this one line, what's the why this number line number 8 have same name as that of this one. This concept is called recursion. The function which calls itself is called recursion. So that's the reason the reason why we have written is this is a kind of tree structure. For after coming as this from 1 to 2, this is again a tree. After coming to node 4, this is again a tree. So we have to make use of this function repetitively inside of after manipulating a node. So each and every time we don't need to write a new functions, we can make use of this existing function. So that's the reason of this recursive call here. So what I'm doing is uh, we can just take the first number. Let me just erase all of this content marks. Okay, here once I come to this first vertex for line number 1, there will be root number 1, there will be 2 and 4. So what I'm doing is I'll take this 2 and then I'll go to this 2 and iterate in this one. After when I'm iterating these number 3, I see whether any number is there associated with that. If there's nothing is there, I'll come out of it and I'll take the next number, which means the 4 will be there. So I'll explain this concept with the use of stack. Internally, the stack will be maintained inside the program stack, but you no need to implement anything. You can just give this one. Okay, now the inside of the content of it is DFS-1. First root node we are traveling and it is inserted. What I have is first is 2, associated with 1 is 2, so I have to insert that also. And then what I have is, okay, I'll just go back to there and I'll explain. Here I have the root as 1, and here what are all the associated with this is 2 and 4. First number I have to take is 2 and then 4. First 2 goes to this vertex, and this vertex is given as a next to root, which means it's become a tree. In this tree we are going to do it 2. Now this will be named as root, and then we are just passing that whole tree as a adjacency matrix. Trace. Okay, I hope you get this one. One we had, and 2 and 4. After, when 2 comes here as a root, we have 2 as a root now, and then 2 will look for what are all attached to it. 2 is only having 3, so it will take us 3, and 3 will be passed as vertex, and next iteration 3 will go as a root, and then it will come. When 3 looks for something is there in that vertex, there is nothing, there is no 3 here in the blue color, so it will just continue this printing this C out. That's the reason the first number is 3 printed in this line. Okay, now how to relate it with the stack? We have first number and then it does 2 went there. I'll erase everything. First we have 1 and then we had 2 and then we have this 3. What we had is this 3. So this 3 is getting inserted. I'm just switching it back to DFS of 3. So this 3 will look for something I have. It don't have anything here, so it will print it. So it will directly go here and print this 3. Okay, now 2 is taken. 2 other than 3, it does not have anything here. Other than this one, it does not have here. So I just took it back to, I'll delete this 3. I switch to pen mode. Here I don't have any, so after this 3 also 2 don't have anything, and 2 also is finished. So I'm just deleting this DFF of 2 After printing this two section, I have this four. I have this DFS, but I completed with all two, and then I have this. I make this color here. We completed it. So, and two also we completed it. Now what I have is four. So I take four. So I'm switching that color as something orange. I just go straight away to 4. I insert it to the snack DFS of 4. What in the 4 is I have 5, I have 6, and I have 7. Then what I have 5, so I have to insert 5. So in 5, after in 5 here you can see nothing is there. So which means that for loop it will not go at all. It just comes print and then it will come out. So if it goes inside of this for loop, then only the recursion starts. If it is not at all there, no elements to iterate, here you can see there is no blue colored I or 5 is there. So it will not go inside of that for loop. So just print that. So 5 is there. So we'll print it and we'll exit. The next is 6. Here also we can turn this color to purple. When 6 is there, 6 also does not have. We just inserted it to the stack. Inserted it to the stack means it's make a recursion call. Inserted is literally mean it make a recursion call. So, okay, now this 6 is also is done. Nothing is there. So we'll print and we'll come out. And then we have 7 having something, so I'll make it as some orange color. I'll go to the 7, so we just make it as inserted the stack 7. So 7, I'm seeing something in the for loop, so it's having something means yes, we have 8. So this 8 also is getting added. So 8, we are checking 8, there is nothing in the child, so it will not go inside of the for loop. So what I'm doing is I'm just printing and coming out. So it's making as completed. And 7 also I don't have, other than 8 I don't have anything. So 7 also completed. So I'm just deleting that and making this color as purple. Okay, after 4 I'm checking for after 7. I don't have anything with nodes attached to this, so I'm making this one also to purple, and I'm printing and I'm coming back, and that's over. After that I don't have anything, like after 4 we don't have anything, so it comes deleting this DFS of 1 and print this 1 also. So we have covered all the children's and all the nodes. That's the reason it's printed as 3 2 5 6 8 7 4 1. That's the reason here we have this uh, sequence we have achieved. Okay, I hope you can get this understanding using the program stack. How do we traverse this one route, and how do we print this algorithm is literally called DFS searching algorithm. There are a lot of algorithms are available. You can use it in the various programs, various upcoming videos. So this algorithm is must. It's just literally 2 lines, but it requires a lot of explanation too for the initial time of understanding. And thank you so much for joining in, and we'll see you in the next video.